Today we'll continue to talk about inverse design in photonics and to talk about a set of optimization technique that we call shape optimization. As a brief recap of what we did last time, we started this discussion about trying to design a photonic device for a specific objective. And in the previous set of things that we did, what we do is we imagine a design region. We break the design region into independent pixels, and then we optimize the permittivity value in each of the pixel in order to meet certain design objective. And so and we went into quite a bit of details in how to parameterize these permittivity values in order to satisfy fabrication constraint, for example, involving minimum feature sizes and so on, that are important to generate a device that actually can be fabricatable. And so this is one very important class of optimization problem. However, there are other ways where you could think about the structure and think about how you optimize it, not necessarily from this pixel by pixel objective, pixel by pixel perspective. So let me give an example. So imagine that you are trying to design a waveguide taper. So you have a narrow waveguide on the left with an input mode coming in, and you hope to go through a region so that it will couple very nicely to a larger waveguide on the right. In doing so, the conventional design would be simply to try to put a taper in between the narrow waveguide and the wide waveguide. And usually then you will control the shape of this taper in order to achieve this objective of mode expansion. So in this case, the natural parameter that you would choose to do is the shape, the interface, as I indicated by the black arrow here. Now, of course, you don't have to do it this way. You can go and do your pixel by pixel optimization. But in many situations, it's perhaps easier to think about this expansion in terms of a taper. And moreover, if you have a three-dimensional structure, for example, then you may argue that there is an advantage of having a taper that looks like this. It is naturally satisfies the minimum feature size requirement usually. And also we have some intuition about what the taper is trying to expand the modes and so on. So that gives you a design that's perhaps easier to understand as it's more intuitive. And the other advantage of this may include that in the case of the pixel by pixel in a 3D structure, you may need to worry about scattering loss. And in here, it is an interface, the scattering loss may actually be lower. So there are things like that you may prefer to think about a structure like this. And as a general statement, as we mentioned last time in this pixel by pixel optimization, ultimately, you are trying to find a structure that satisfies certain constraint, in these cases, the constraint, in fact, can be trying to come up with a design that is maybe slightly more conforming to human intuition. So in this case, then, what you would need to parameterize is the position of the interface between the high dielectric region and what's outside and in air. And then you would need to compute the derivative of the objective function with respect to the position of the interface. I won't go into detail. There's a paper a number of years ago that show you how to compute this particular derivative that gives you the gradient But I will just simply point out that the formula here, to give you some flavor of what the math look like, the t here is some sort of objective function that you care about. The s is a parameter that parameterize either the position or the orientation of the interface in the computational domain. And the derivative of the objective function with respect to this parameter that parameterize the geometric information interface, in the end, is related to certain kind of integral of both the parallel field, the field that's parallel to the interface, and the perpendicular field. It turned out that you need to treat the parallel field and the perpendicular field differently because they have different boundary condition. But if you do it right, then you actually can compute this derivative, and that derivative gives you the gradient information for which you can then use to further optimize the structure. So let me give you an example of the optimization process. In this case, we consider a waveguide band. This is the waveguide geometry, the cross-section view of the waveguide. This consists of a silicon nitride region sitting on top of a silicon dioxide substrate. And then outside the nitride region, there's also an air region. So this nitride waveguide sits at the interface between air and silica. And so on the left here is the top view of this device. So what we're trying to do is to construct a waveguide band. Now, the width of these waveguide is chosen so that, in fact, this is a multimode waveguide. But what we like to do is to excite the fundamental mode of the waveguide, for example, by a source at the green curve here, and then have this fundamental mode propagate through the waveguide band, so that when it reach the other end of the band, it remain in the fundamental mode with high efficiency. So that's the designing objective. And with that, you can then write an objective function. Now, the key then is to try to parameterize the interface, the shape of the interface here in terms of a differentiable parameter. So the way we do it, we can truncate, or rather divided, this waveguide bending region into different section, into different rectangular section, or and then each of these sections has an outer and an inner boundary and the width associated with it. Then we can compute the derivative of the objective function with respect to these width parameter, using what I've talked to you just now about this technique of computing derivative in terms of the shifting boundary. So now, as usual, we would like to impose fabrication constraints associated with this geometry. So one of them is that you can, in fact, choose so that the inner and outer radius of this boundary would not be either too large or too small. And so you could actually constrain the waveguide band region only in a certain region of the space. And this can be done by basically using this hyperbolic tangent function to restrict where the inner and outer boundary is in a narrow value range. So as we mentioned last time about these hyperbolic tangent function, this is a very useful function to impose a cutoff of certain value, but in a smooth way so that you can take derivative. Also, in the fabrication, you quite often do not want to have too sharp of a bend. And so, therefore, one can impose also a radius of curvature penalty with a penalty function that looks like this. So as we vary the boundary of the inner and outer edge of this waveguide, the local radius of curvature will change. And what this penalty ensures is that the radius of curvature really does not fall below a threshold as indicated by R0. And when it's significantly, the radius of curvature is too small, then this penalty function will start to kick in. So with that, here is the visualization of the optimization process. So on the left here is you see the top view of the starting device, and that's just basically drawing two circles. And on the right, you see the performance of this starting device. So you can see that we excite a fundamental mode here by putting a source on the green curve here, and you see that the excited mode at the input end look very much like a fundamental mode. It's centered. The field distribution is centered at the center, geometric center of the waveguide. When it passes through the waveguide band, you can see that, well, most of the energy does pass through, but you can see substantial amount of energy gets shifted away from the center that indicate that you generate quite a bit of higher order mode on the other end. And now we run the optimization process. So on the right here, we show the objective function as a function of iteration number. And you can see, and we started from here, and I show you the field distribution. As we run the iteration, the objective function gradually improves. And at the end, you get a very high transmission efficiency going to the fundamental mode of the output waveguide. And this you can see in the how the optimized function look like. And on the output facet, you see that the field now is largely centered at the geometric center of the waveguide that give you one indication that you are strongly exciting the fundamental mode in the output end. And if you compare the structure of the input structure and the output structure, you can see this subtle shift in both the outer edge and the inner edge of the waveguide. And as a result, neither of them is a circular object anymore. And that shift is enough to give you very substantial improvement of the objective function. But in the meantime, it generates a structure that perhaps has some intuitive appeal. It is just like a regular waveguide, but with small adjustment. And it is also a structure that doesn't have very sharp curvature, doesn't have small pixels, and therefore potentially can be more amenable for nanofabrication. So here we give you a sort of a movie of the optimization process. You can see how the boundary between the silicon nitride and air get adjusted and how that translates into the field distribution inside the waveguide being varied. So to summarize this part of the presentation, we give you a discussion of an alternative idea for optimization. So instead of doing pixel by pixel optimization, you can also do shape optimization, where you change the shape of the interface alone. And in many waveguide problems, this is in fact a quite effective strategy to allow you to generate a structure that is amenable for nanofabrication, and in the meantime, perhaps has better connection to human intuition and ideas in standard waveguide design. So with that, let me stop here.